For decades, the idea of powering devices without a single cable seemed like pure science fiction. We imagined a future where energy flowed invisibly, effortlessly, through the air around us. Today, that futuristic concept is rapidly evolving into a tangible, practical reality. Wireless energy transfer, or WET, is poised to fundamentally revolutionize how we power our myriad electronic devices. It promises to free us from the tangle of cords and the constant search for an available outlet. This technology is not just about convenience. It's about a paradigm shift in energy delivery. At its core, wireless energy transfer is the transmission of electrical energy from a power source to an electrical load without the need for physical wires or conductive connections. It leverages fundamental principles of physics to make the invisible flow of power possible. The benefits are profound, offering unprecedented convenience, flexibility, and even new design possibilities for electronics. While still in the early stages of widespread adoption, WET is already making its way into our daily lives. From charging our smartphones on a pad to powering electric toothbrushes, the seeds of this revolution have been sown. Its immense potential spans across countless applications, from small personal electronics to large-scale industrial machinery, and even electric vehicles. The journey towards a truly wire-free world is underway, driven by continuous innovation and a growing demand for seamless power solutions. Understanding the mechanisms behind this technology is key to appreciating its impact. We are witnessing the dawn of a new era in energy, one where power is as ubiquitous and accessible as Wi-Fi. Wireless energy transfer fundamentally relies on the principles of electromagnetism, a cornerstone of modern physics. The interaction between electric currents and magnetic fields is what makes this incredible feat possible. By manipulating these forces, energy can be projected through space. Several key methods have emerged for achieving WET, each with its own strengths, limitations, and ideal applications. These methods vary primarily in their range, efficiency, and the type of electromagnetic field they utilize. Understanding these distinctions is crucial for grasping the full scope of WET. The most common and widely adopted method currently is inductive charging. This technology is familiar to many through wireless charging pads for smartphones and smartwatches. It operates on the principle of electromagnetic induction, discovered by Michael Faraday. Inductive charging utilizes a transmitter coil, often embedded in a charging pad, to generate an oscillating magnetic field. When a compatible receiver coil, located within the device to be charged, is brought into close proximity, this fluctuating magnetic field induces an electric current within the receiver coil. This induced current then powers or charges the device's battery. The efficiency of basic inductive charging is high over very short distances, typically a few millimeters. This makes it ideal for applications where devices can be placed directly onto a charging surface. Its simplicity and reliability have made it the standard for many small consumer electronics. A more advanced form of inductive charging is resonant inductive coupling. This method significantly improves upon basic induction by increasing both efficiency and the practical range of energy transfer. It achieves this by tuning both the transmitter and receiver coils to resonate at the same specific frequency. When two objects are tuned to the same resonant frequency, they can exchange energy much more efficiently, even over slightly greater distances. Think of it like pushing a child on a swing. If you push at the right frequency, the swing goes higher with less effort. This resonance allows for more effective energy transfer, reducing losses. Resonant inductive coupling enables energy transfer over distances of several centimeters to a few meters, depending on the power level and design. This opens up possibilities for charging devices that are not in direct contact with a pad, such as a laptop on a desk or a device across a room. It represents a significant step towards more flexible wireless power. Another promising method is radio frequency, or RF transmission. This approach uses radio waves, a form of electromagnetic radiation, to transmit energy through the air. Unlike inductive methods that rely on near-field magnetic fields, RF transmission uses far-field radiation. RF transmission has the potential for much longer-range applications, theoretically capable of powering devices across entire rooms or even buildings. This is because radio waves can propagate over significant distances. Imagine a future where your devices are constantly topped up with power, no matter where they are in your home. However, RF transmission is often characterized by lower efficiency compared to inductive methods, especially over long distances. Much of the transmitted energy can dissipate into the environment or be absorbed by obstacles. Directing the energy precisely to the receiver is also a challenge, often requiring beam-forming techniques. Despite the efficiency challenges, the long-range potential of RF transmission makes it a subject of intense research and development. It could enable truly ambient wireless power, where devices are always charged without any conscious effort from the user. This method holds the key to a future of pervasive wireless energy. Each of these methods, inductive, resonant inductive, and RF, plays a vital role in the evolving landscape of wireless energy transfer. They offer a spectrum of solutions for different power needs and distances. The ongoing innovation in these areas is what will ultimately bring about a truly wire-free world. The advantages of wireless energy transfer extend far beyond mere convenience, touching upon aesthetics, safety, and practicality in diverse environments. One of the most immediately apparent benefits is the elimination of cable clutter. Our homes and workspaces are often overrun with a spaghetti of wires, each serving a specific device. WET promises to untangle this mess, creating cleaner, more organized spaces. Beyond aesthetics, WET offers significantly enhanced charging convenience. No more fumbling for the right cable or searching for an available port. Simply placing a device on a surface or bringing it into proximity with a transmitter can initiate charging. This seamless experience integrates power delivery into our daily routines without conscious effort. The improved aesthetic appeal of a wire-free environment is undeniable. Devices can be designed with fewer ports, allowing for sleeker, more minimalist forms. Furniture can incorporate charging capabilities, turning everyday surfaces into power hubs. This integration makes technology feel more natural and less intrusive. Wireless energy transfer also brings increased safety by removing the risk of electrical shocks from exposed wires or damaged insulation. There are no physical contacts to corrode or short circuit, reducing potential hazards. This is particularly beneficial in environments where water or dust might compromise traditional wired connections. Furthermore, WET offers unparalleled practicality in environments where wired connections are challenging or even dangerous. Consider medical implants, such as pacemakers or neurostimulators. Wireless charging eliminates the need for invasive surgeries to replace batteries, significantly improving patient quality of life and reducing infection risks. Another compelling example is underwater applications. Powering sensors, remotely operated vehicles, or even subsea equipment wirelessly removes the complexities and vulnerabilities of waterproof connectors and cables. This enables more robust and reliable operation in harsh marine environments. The ability to transfer power without physical contact opens up entirely new possibilities for design and deployment in challenging settings. Despite its immense promise, wireless energy transfer faces several significant challenges and limitations that researchers and engineers are actively working to overcome. One of the primary concerns is efficiency. During the transmission of energy through the air, some power is inevitably lost to the environment. This energy loss means that not all the power put into the transmitter reaches the receiver, leading to lower overall efficiency compared to direct wired connections. Another major limitation is range. Most current WET technologies, particularly the highly efficient inductive methods, require devices to be in very close proximity to the transmitter. While resonant inductive coupling extends this range somewhat, truly long-distance wireless power remains a significant hurdle. The further the distance, the more energy dissipates, making efficient long-range transfer difficult. A critical challenge for widespread adoption is the lack of standardization. Different manufacturers often use proprietary WET technologies, hindering interoperability between devices and charging solutions. This fragmentation means that a wireless charger from one brand might not work with a device from another, creating consumer confusion and limiting market growth. A universal standard, similar to USB for wired connections, is essential for seamless integration. Finally, there is a pressing need for robust safety regulations. As WET becomes more prevalent, it's crucial to ensure that these systems do not interfere with other electronic devices, such as medical equipment or communication networks. Additionally, potential health risks associated with exposure to electromagnetic fields, even at low power levels, must be thoroughly researched and addressed with clear guidelines. Public trust and acceptance depend on rigorous safety protocols. Addressing these challenges, improving efficiency, extending range, establishing standards, and ensuring safety, is paramount for WET to reach its full potential. Significant research and development efforts are focused on these areas, paving the way for a more ubiquitous and reliable wireless power ecosystem. The future of WET hinges on overcoming these technical and regulatory hurdles. Despite the current challenges, the future outlook for wireless energy transfer is incredibly promising. The limitations we face today are driving intense innovation and research, pushing the boundaries of what's possible. We are on the cusp of a transformative era in power delivery. Ongoing research and development efforts are laser-focused on several key areas. Scientists and engineers are tirelessly working to improve the efficiency of WET systems, aiming to minimize energy loss during transmission. Breakthroughs in materials, science, and circuit design are continuously enhancing power transfer capabilities. Simultaneously, significant progress is being made in increasing the transmission range of wireless power. While truly ambient, room-scale power is still a long-term goal, advancements in resonant coupling and directed energy transfer are steadily extending practical distances. This will enable more flexible and convenient charging solutions. Furthermore, there is a strong push towards developing more versatile and standardized WET systems. Industry consortiums are collaborating to establish universal protocols, ensuring interoperability across different devices and manufacturers. This standardization will be crucial for widespread consumer adoption and market growth. As the technology matures, we can expect WET to be integrated into an ever wider range of devices and environments. Imagine household appliances that power themselves simply by being in a kitchen, or furniture that charges your devices without visible wires. The home of the future will be a truly wire-free zone. The impact on electric vehicles will be particularly profound. Wireless charging pads embedded in roads or parking spots could allow EVs to charge passively while driving or parked, eliminating the need for cumbersome charging cables. This could significantly accelerate the adoption of electric transportation. Ultimately, wireless energy transfer is anticipated to transform our fundamental methods of power delivery. It will move from a niche feature to an invisible, ubiquitous utility, much like Wi-Fi is today. This shift will redefine our relationship with energy, making it seamless and always available. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.